Hey, welcome back to Math with Patrick. It is March 7th. We have problem number 66, and I recognize this kind of problem. We have a system of equations. I want to solve this 3 different ways and show you how you might solve your own system of equations using whichever method feels best to you. So let's get into it. Let's try substitution first. I like to think of substitution as like that part in the Indiana Jones movie where he like measures out a sandbag that weighs exactly the same as an idol. You like swap them out and you don't set off the traps, unlike a lot of the movies. And the idea here is that you wanted to replace or substitute one thing for its equivalent, in this case in the movies, equivalent weight. With substitution in systems of equations, I want to substitute one of the variables for an equivalent expression. Now I'm solving for x today. X is supposed to be 7. And so ideally, I'm going to substitute out the y and only have x's so I can solve for x and get 7. And the first idea here is I would like to figure out what y is equal to in terms of x. So I want y is equal to something. And I'll take that something and I'll stick it right here. And then that way, I'll have x's and another thing with x's, and I can just forget about the y's. I mean, oftentimes you go back and solve for y, but we don't have to do that here. So from this first equation, I could subtract an x from both sides. So saying y is equal to 13 minus x is equivalent. I'm just subtracting an x here and subtracting an x here. And this lets me do my substitution move, where I see the y in the other equation, and I just completely replace it with this expression on the right side of my equation, because y is the same thing as 13 minus x, so I can replace the y with 13 minus x. Now I'm just solving a one variable equation. I think the best thing to do here is distribute the 5. And so 5 times 13 is going to be 65. And then 5 times a negative x will be minus 5x. Let's see. Let's combine some like terms. The 10x minus 5x is just 5x. And let's just do it one step at a time. I'll keep the 65 here for now. I know that something plus 65 is 100. You can rethink this by just subtracting a 65 from both sides. Essentially, this 5x must be a 35 for this above equation to be true. This says 5 times something is 35, and just because I know my times tables, I know that x is going to be 7. You could also think about maybe dividing both sides by a 5, and that would also result in the same answer. X is 7. So that was substitution. Let's also try elimination on this page, and then I have one more strategy, and I'll open up a new tab for it. So elimination works a little bit differently. The idea here is I want to add or subtract a whole equation from another one. And my goal here is to eliminate or get rid of one of my variables, kind of like how I did here. I eliminated the y by using substitution. Here, I also want to eliminate these y's, and my strategy instead will be adding or subtracting these equations from each other. If I just tried it right now and I subtracted, say I take this whole equation, I could subtract an x and subtract an x and subtract a 13. And I'm allowed to do this because x plus y is the same as 13. So if I, so if I take away an x and a y, I could also equivalently take away a 13. Now this doesn't really help me because I get 9x plus 4y is equal to 87. This is a true equation in this system here, but my goal was to eliminate my y's. I want to solve for x. I want to get rid of y. So beforehand, I would like to line up these y's and get a 5y right here so that these will cancel out. So my first step is I'm going to line up my y's together by multiplying both sides of this equation by a 5. And I guess I'll show my steps like this. I'll go times 5. And so if I increase one side of an equation by 5 and the other side of an equation by 5, I'm not going to change the fact that they're equal to each other. So 5x plus 5y is going to be equal to 65. You might note that 65 did show up in the other example, and so there's a little bit of overlap between these two strategies. Okay, and then I want to take my 10x plus 5y equals 100 equation and take away the 5x and the 5y and the 65 that I'm getting from my second equation. Here, 5y minus 5y is 0y. You don't have to write that. I'm just doing it to show my work. 10x minus 5x is 5x. And then 100 minus 65 is 35. So already I've just essentially gotten to the exact same part. This 5x equals 35. And then I can divide both sides by 5 and get x equals 7. So depending on the kind of problem you have and depending on your preferences, you could use substitution or elimination. And let's do the last method, graphing. To me, this is probably the easiest way to solve systems of equations because not only can you solve linear equations, you could even solve like quadratic systems of equations. So like this one, you could just solve by graphing, and it looks like we do get these non-whole numbers. This one's actually kind of close to pi. That's just a coincidence. So if you do get these like non-whole numbers, maybe it would be useful to actually do the algebra and figure out like why we're getting 3.14 or something. Like that way you could confirm with yourself that it has nothing to do with pi, it's just a coincidence. Anyways, back to the current problem at hand. With systems of linear equations, you might notice that, well, we have two lines, and really the only interesting part is where they intersect, because they're just kind of always going away from each other, but they do intersect somewhere. And this is a visual representation of what we just found. These x and y values that correspond to this point are the only shared x and y values. As in, this blue line represents all the different other x and y values that satisfy the bottom equation. And then the red line represents all the different x and y values that satisfy the top equation. Like here you can see, 0 plus 13 is 13. Here, let's see, this one, if you set x equal to 10 and y equal to 0, you can see that 100 plus 0 is 100. The only spot where they agree is where the lines are going to intersect. So right here, you can see that the x value is 7. We already saw that with substitution and elimination. And also just some bonus points. Now we know that y is going to be 6. And we could have found that back on our other document, but here we're finding it by graphing instead. So those are my 3 different ways to solve systems of linear equations. Ultimately, we get that 7 is the answer. That's today's state. And so we were already done, back when we found the number 7, but I figured, why not? Let me show you 2 other options. So thanks for coming along. That's all for me today. And I'll see you tomorrow. Okay, bye.